This is lecture 9.2, which is the beginning actually of equilibrium with acids and bases. So we're going to put together what you learned about pH and pOH and concentrations and things like that with what you know about equilibrium and equilibrium constants. And we're going to learn about Ka, which is the equilibrium constant for a weak acid at equilibrium. So the learning targets are here. If you haven't done them yet, please make sure that you get yourself started with this, and then I'll have some examples and a few things to add as you watch this lecture. So when you're ready, go ahead and stop the video and restart it. Okay, so let's see what we can do. So the things that you should have learned now about K from your learning targets, Ka is the equilibrium constant that represents the equation of a weak acid at equilibrium with its conjugate base. And so usually we include the water for that in the equation, and we kind of go from there. So I kind of jumped the gun here just a little bit, but what you're looking at is your equation is going to be one of two things. It can be in this version where you have your weak acid plus water forming the hydronium ion, because this is a Bronsted-Lowry situation, and so the acid's going to donate the hydrogen to the water, forming the hydronium ion and leaving behind the anion of the acid, which is the A-. So weak acids will do this when we put them in water, and you can choose whether you want to write the water in the equation and have it show as hydronium, or whether you want to not write the water in the equation and have the H+, which is equivalent to the hydronium ion as you're working there. Okay, so you can decide. When we do weak bases, you have to have the water in the equation, but and most of the time College Board includes the water in their equation for weak acids, but it's just something that you see both ways, and so I kind of wanted to make sure that you were aware of that. You write the Ka the same way as you would write the K for any other equilibrium system, and so in this case Ka would equal the concentration of the product, which would be the hydronium ion in aqueous solution, and the anion, the A- or the conjugate base ion, over the water as a liquid, so only over the concentration of the weak acid, which is a molecule dissolved in water. So this will be in the aqueous state. Okay, so this is what Ka would look like, and Ka's for weak acids are always less than 1, meaning that the weak acid in molecule form is predominant in the equilibrium system. All right, so we can do the same thing for weak bases. They have Kb's, which would be the same idea as the base or the conjugate ion. So something that you need to be really careful of is that now that you've practiced a little bit in class with conjugate pairs, the Ka of the K of the weak acid and the Kb of the conjugate base are related to each other, and it's really helpful to know this because we use this a lot in acid-base equilibrium, especially once we start titrations. So you can find the Kb of the conjugate base, or you can find the Ka of the conjugate acid by using Kw. So the relationship that you've already worked with is Kw equals the hydronium ion concentration times the hydroxide ion concentration. Well, Kw also equals Ka times Kb, as long as the acid and the base are conjugates of each other. So remember that this would have to be the conjugate base. So if we're looking back at this equation, this is your weak acid, the Ha, and the A- is the conjugate base. So in this case, what we could say would be the Ka of Ha times the Kb of A- would be equal to 1 times 10 to the negative 14th. This is a really important relationship, so put this into what you have in your memory, just like you did the calculations for pH and pOH. And of course, then, to make it the P of instead of the negative exponent of the negative 14th as your relationship, we can do the same thing as we did with pH and pOH from H3O plus and OH minus. So 14 equals the pKa plus the pKb, and the pKa is just the negative log of the Ka of the weak acid, and the pKb would be the negative log of the Kb of the conjugate base. Conjugate is a J, sorry, conjugate base. Okay, so these relationships are to get you ready to start working. I do want you to look at this as some examples so that we can kind of talk about how this helps us to know some things. And so in the conjugate pair, notice that this pair of ions is related to each other by a difference of only one hydrogen, so this makes them a conjugate pair. But both of them could act as an acid or as a base. They're both what we call amphiprotic. And so technically the H2PO4 minus could lose a hydrogen and become HPO4 minus, or the HPO4 minus could gain a hydrogen as a base and become HPO4 minus. Or we have to kind of think really carefully here about the relationship between these, okay? So from what's happening is we could definitely, if we had both of these just in water solution, we could have to make a decision about which one was a stronger weak acid, etc. And you could do that from the Kas of the two of them. And so definitely notice that the Ka of HPO4 minus is greater than the Ka of H2PO4 minus is greater than the Ka of HPO4 minus, which means that the H2PO4 minus is a stronger weak acid, still weak, still mostly the molecule, but stronger weak acid than the HPO4 minus is. And so because of that, where the H2PO4 minus is more likely to be the weak acid, then in this situation, in our equation, we would definitely know that this is the weak acid and this would be its conjugate base, okay? Something else that we can do is calculate the information from the Kas. And so I want to show you this in an example because I think it's important that you see it. So the Ka of ammonium, the ion, is 5.6 times 10 to the negative 10th, and it wants several things in this question. So the first thing is, what's its pKa? So the pKa would be the negative log of Ka, which in this case is the negative log excuse me, of 5.6 times 10 to the negative 10th, which then equals 9.2557255. Can't read my own handwriting. Maybe that's a 27. Okay. And so we need to remember that when we take the negative log of something, our two significant figures become two places after the decimal. So this would be a pKa of 9.26. I can find the Kb by either I could find the pKb by subtracting the pKa from 14, which is a fast way to do it, but I can also do the Kb from the Ka, and usually this is what I do when we're doing buffer calculations. So I'm going to practice that with you. And so remember that the Kb would equal Kw, which is 1 times 10 to the negative 14th, divided by the Ka. And so the Kb would then, at this point, be 1 times 10 to the negative 14th, divided by the Ka we were given at 5.6 times 10 to the negative 10th. And that gives us 1.7857 times 10 to the negative 5th. I have two significant figures, so this is going to be 1.8 times 10 to the negative 5th equals Kb. All right. And then finally, if I want pKb, I can either come and subtract the 9.26 pKa from 14, or I can take the negative log of Kb. So pKb equals the negative log of Kb, which equals the negative log of that number. And when I punch that into the calculator, I get 4.74818, a bunch of numbers. My two significant figures will show up after the decimal now, so the pKb would be 4.75. Okay, so this is how you use that information to go back and forth. And I know it doesn't seem like it's important right now, but it's going to be an extremely important relationship. So you definitely want to make sure you know how to do this. Okay, all right, so let's see what's next. The way that we work this is that you have two things that you can do using Ka, just like you had two things that you could use in Kc or Kp. You'll often need to write the equation. You'll need to write the Ka expression, which would be this, and then you'll need to write your ice chart, because most often you have to picture that when you dissolve the acid, it is an initial situation, and you don't have any of the hydronium ion or the conjugate ion. And when it reaches equilibrium, you will have some of the hydronium in the conjugate. So the thing that you need to remember is that instead of asking you for the concentration of the hydrogen ion or the hydronium ion or the conjugate ion, usually what we care about this is a way of determining pH. And so the ion that you care about in your ice chart would be the H3O plus or the H plus if you haven't included the water. And this will equal X on your ice chart. Okay, so we'll look at this and I'll show you what this means. So there's two different ways you can do this. I can either give you hydronium concentration and ask you to find Ka, or I can give you Ka and ask you to find hydronium concentration or pH. Okay, so kind of just keep this in mind. If you're going to find pH, you're going to ice it. You're going to use Ka to solve for X, which then equals the hydronium concentration. So you can take the negative log. And if you're given pH and asked to find K, then you can do 10 to the negative pH to find the H3O plus concentration. And then that matches up with your E line of your ice chart, and you can substitute everything in for the E line and set it equal to Ka to solve. All right, so let's do a couple of examples, but I do want to talk about one thing that's a reminder. The 5% ionization or dissociation rule means that when you don't have a perfect square, and now you will not usually have perfect squares because the coefficients in our equations are all 1, okay? So you won't have perfect squares here. You have an acid molecule forming 2 ions. So the thing that you want to think about is the X that would require to use the quadratic, which is going to be the minus X in your weak acid, okay, is the one that you can cross off. And this is because Kas are often small, but they're not always super small. And the percent dissociation also depends on the concentration. So if you have a small concentration and a relatively large Ka, you may actually need the quadratic. I don't think College Board will make you do that, but you should definitely know how to check for it. And they do use percent ionization or percent dissociation a lot. So you need to know that your ion at equilibrium, we do the same thing for weak bases, but what we're going to do today is for weak acids. So the ion concentration that we're talking about here is the H3O plus ion concentration over your weak acid initial concentration, okay? This would be your weak acid in the initial line, and this would be your hydronium concentration at equilibrium. So it's basically how much did it dissociate compared to what you started with. How much did it dissociate compared to what you started with times 100 to make it a percent. And if it's less than 5%, then you can cross off the X, which you would have already done. You can leave it crossed off and know that your answer is okay. If it's more than 5%, then you would have to put the X back in and use the quadratic to solve. All right, so let's do a few. The thing that you have to remember is that you have to identify first if it's a weak acid, and if it is, you need your ice chart, you need your equilibrium equation, you need your equilibrium expression. And from that, then you're going to decide what they want you to do. So this says, calculate the percent dissociation of HCN. HCN is a weak acid. They give you background that tells you it's in the pits of cherries and apples, and they give you its Ka, and they want the percent dissociation and the calculation of the pH. So the percent dissociation, we definitely need our equation. So I'm going to write HCN plus water at equilibrium with the hydronium ion, because this H is going to transfer, and the cyanide ion. So the cyanide ion is the conjugate base. And I'm going to write Ka equals H3O plus times cyanide concentration over HCN concentration, because those are my three things that are aqueous in solution. The water is a liquid, so I'm going to ignore it in my ice chart. My initial concentration of HCN is 0.75 molar, and that means that when I first put it in there, before it does anything, I have no hydronium, at least nothing appreciable. There's some from the water, but we ignore it because it's small enough that it doesn't make a difference, and no cyanide. This means that because I have zeros, my reaction is going to proceed toward the zeros. So this would be minus X plus X and plus X. And you're going to really like this because there aren't coefficients and exponents. And that means that when you go back to review Kc, Kp, and Ksp, you have to be more careful about coefficients than you were the first time around. That means my equilibrium line will be 0.75 minus X and X and X. And now I can decide how to figure out the percent ionization. So this means that I need to solve for X, because percent dissociation or percent ionization is going to be X over the initial concentration of the HCN times 100. And I know the initial concentration of the HCN is 0.75, but I don't know the X, and so I need to solve for that to figure that out. All right, so I need to be solving for this. So I'm going to use my Ka to solve for this. They gave it to me. So I'm going to say Ka equals 6.2 times 10 to the negative 10th. And that would equal the hydronium, which is X, times the cyanide, which is also X, over the hydrocyanic acid, which is 0.75 minus X. All right. And now this is the X that we're talking about that's going to make this really ugly, because this would require the quadratic. We're going to cross off the minus X. And I can now take the square root of, I can cross multiply here, right? I can cross multiply my 0.75 times 6.2 times 10 to the negative 10th, and then take the square root of that, and I find that X equals 2.1564, some more numbers, times 10 to the negative 5th. And I need to find my percent ionization. So I'm going to round that. I think it doesn't really matter. I can leave it in long, or I can round it. I think in my own calculations, I did it as 2.2 times 10 to the negative 5th. So I'm going to figure that out, divide that by the initial concentration of the cyanide ion, or the hydrocyanic acid, times 100, and it comes out to a really small percent, 0.0029%. That's after I multiplied by 100. So this is definitely okay to leave the X crossed off. All right, so that's how you figure out percent ionization if they ask for it, and it's how you verify that it's okay to cross off the X. Usually the rule is that if your concentration and your K are different by a factor of 100 or more, you're okay. So by 2 exponents, usually more than 2 exponents, then you're usually okay. So this would be 0.75 is 7.5 times 10 to the negative 1st, and the Ka is 10 to the negative 10th, so those are definitely far apart. But if you need to solve for percent ionization, this is how you do it. Okay, now they also want pH, so I have to remind myself that the X is the hydronium ion concentration at equilibrium. So that means that if I want pH, it's going to be the negative log of X, because this is the hydronium at equilibrium. Okay, so I'm going to take negative log of X, and I just usually leave it in my calculator and use it. And when I do that, I get 4.666 27, maybe some more numbers after that. I have 2 significant figures, so that means that I'm going to keep 2 places after my decimal in my pH, would make it 4.67. Okay, all right, let's try another one, and then I know this is going to be a long lecture. I have a few other things I need to talk about with you. So in this example, we're going the other direction. We're going to find Ka. They tell me I have a weak acid. They tell me the pH of the solution, and anytime they say that pH is measured when it's at equilibrium, because by the time you get the pH meter in there, it will have reached equilibrium. So you have to know that. It's just like a saturated solution in KSP is at equilibrium. Anytime you're measuring a pH, it's at equilibrium. So they want Ka, and I know this is my initial solution concentration. So I'm going to need my equation, NH4 plus, if they tell me it's a weak acid, you should be able to identify that on your own, plus water, gives me, actually I'm going to do this one without the water, because sometimes you'll see that. So we can just say that the ammonium ion is at equilibrium with the ammonia ion and the H plus ion, or the ammonium molecule, and the H plus ion. If you wanted to, you can always write it as NH4 plus water yields NH3 plus H3O plus, because that's what's happening, is this is donating the hydrogen to the water. Okay, and these are equivalent equations. So so I'm gonna ice this, and my initial concentration, there's 1 NH4Cl, or 1 NH4 and NH4Cl, so my initial concentration is the same, 0.2 molar, and there's none of the other 2 ions before it does anything. I'm going to do minus X and plus X and plus X. If I were doing it over here, this would be 0.2 and 0 and 0, and the same thing, minus X plus X plus X. This is 0.2 minus X and X and X. And now I need to figure out what X is so that I can solve for Ka. So I'm going to say Ka equals the ammonia times the hydronium over the ammonium concentration. And this would then equal Ka will equal x squared over 0.2 minus x. And this time I'm not going to cross off the x because I need to solve for x. So to solve for x, I have to know that the pH is coming from the hydronium ion concentration. So remember that if I want hydronium concentration, it's equal to 10 to the negative pH. So I can say that equals 10 to the negative 5.0. And that would be equal to X because there's my hydronium or my hydrogen ion concentration. Okay, so I can come back in here and say this is 1 times 10 to the negative fifth. I have 2 sig figs there, but only, oh, sorry, I have 1 sig fig because this is a pH of 5.0, so only the 1 digit after the decimal is significant, and I only have 1 sig fig in my concentration anyway. So 1 times 10 to the negative fifth squared over 0.2 minus 1 times 10 to the negative fifth. And I can solve for Ka. And this time I actually am going to leave that in there and let my calculator do the work for me rather than crossing it off since I know it. And that's going to give me 5.00025 times 10 to the negative 10th. And that means that with one significant figure, this is literally now 5 times 10 to the negative 10th equals Ka. So those are your examples for how this works. All right. And we'll do this in practice with this in class. All right, the last few things are theory, so I just want to kind of touch on them. I know they should be in your learning targets already, but there's some of the more confusing theory in this unit, so I do just want to touch on them a little bit. If you have a polyprotic acid, that's one that has more than one hydrogen. So this is examples like H3PO4 or H2SO3. H2SO4 technically, but remember that the first hydrogen is strong, 100% ionizes in sulfuric acid. So these are examples because they have more than one hydrogen. This means that when they ionize or dissociate, they do it one hydrogen at a time, which technically means the complete dissociation is a sum of multiple equations. Okay, so if somebody asked you for the complete dissociation of one of these, they would have to tell you Ka1, Ka2, Ka3, and to find the total Ka of the 100% ionization of this, or the 100% dissociation, the equation where you've got no hydrogens left. So in other words, like H3PO4 plus 3 water at equilibrium with PO4 3 minus and 3 hydronium ions. If you wanted to do that, technically that would be Ka1 times Ka2 times Ka3, because that would give you your overall Ka, because that would be adding together the 3 ionization equations. All right, the 3 dissociation equations. So that's the first thing I wanted to touch on. The second thing is that when we do this, you have to trust me, but if you don't believe it, we can talk about it and prove it together. But because the Ka2 is so much smaller, this is because of Le Chatelier and common ion, and I want to show you that, and because of significant figures, if you want to figure out the pH of a polyprotic acid, the hydronium ion concentration and the pH come only from the first ionization, and you're only worried about Ka1 at that point. Okay, so this is because of a few things. So let's just say I have a 1 molar solution of oxalic acid, and I'm not worried about the water, and these start at 0. So when it goes to equilibrium, these will be minus X and plus X's, and this will be 1 molar minus X, and these will both be X. Right? So I could find the pH of this by calculating the negative log of X, because that's the hydronium concentration. Or I could say that this is the hydronium concentration that's contributed because of the H2C2O4. But notice that this ion then can also be a weak acid, and so it starts a second ionization. But when we do this one, the concentration of it is my initial X from here, right? And I have no oxalate, which is great, but at the start of this, I also have, oops, sorry, I drew this arrow in the wrong place. Hang on. What happens is this oxalic acid, or this oxalate, hydrogen oxalate, I don't know what we call this ion, right? But this concentration is coming from here. But notice that you actually have hydronium ion concentration in a significant amount in solution. So that one has to come here. And then there's no oxalate. So now when you do this, notice this is like a common ion. This is like trying to dissolve something in KSP in a solution that already has one of those ions there. So these are actually there in equal quantity right now, and that means that it's going to be very difficult, according to Le Chatelier, for this to move forward, which means that the equilibrium is only going to move forward slightly. And this is why the second Ka is smaller than the first Ka. Okay, so because of that, and because any differences that we see will usually be beyond our significant figure and our measurable values, you can only worry about the Ka number 1. So that's first, okay? The next thing I want to touch on that's kind of confusing is your trends in acid strength. And this is going to be something that you may be asked to explain in a free response question. It probably, or pick out in a multiple choice question, it might be 2 points total or 3 points total in the whole exam. But if you can try to understand it, that will be helpful, because that will help you as you're trying to gain some points. So the first thing you want to know is that across the periodic table, and when you have same number of oxygen, but different nonmetals, all depends on that different nonmetal in the center. And as you go across, electronegativity increases, and that pulls the electrons in the H to X bond away from the H and toward the X. So it makes it more polar. And as a matter of fact, it almost pulls them 100% of the way, which would then weaken the bond, because it is no longer a covalent bond, and allow that to ionize, okay? So remember that the more easily removed a hydrogen is, the stronger the acid. And that's kind of weird. You have to picture that. The more easily it's removed, the stronger the acid, the greater percent ionization. All right, so when you're looking at across the periodic table, or you're looking at two like sulfurous acid and nitric acid, where these are both with 3 O's, then what you're talking about there is the idea that having the different electronegativities of sulfur and nitrogen will mean that nitrogen with 3 O's is nitric acid, which is actually a strong acid, but sulfurous acid with 3 oxygens is a weak acid. Okay, so we can see that. That's the first thing I want to talk about with this. The second thing is notice that with these oxo acids, the ones with polyatomic ions, the hydrogen is attached to the oxygen, not to the nitrogen or not to the sulfur. So one of those oxygens has that hydrogen attached. This is always the case, and when we drew Lewis structures, you may not have drawn them this way. So you definitely want to picture that this is what's going on. So if you have more oxygens attached to the center atom, then what happens is that this center atom, the oxygens are always more electronegative than the center atom, and the center atom actually has these electrons that are pulled toward the oxygen and away from the sulfur, which delocalizes the electrons more, polarizes this bond more toward the oxygen, because the oxygen will be really much more negative, making it easier for the hydrogen to come off. All right. And then finally, the last thing would be down the periodic table. This is because of a longer bond length, because of a bigger atomic radius. And we all know that longer bonds are weaker bonds, which means that the hydrogen is removed more easily. So this is confusing. And if you need to reread what I have here, it's different than the way your book says it. If you need to re-listen to this section of the video so that you understand it, that might be an important thing for you to do so that you can know that you can explain it correctly in free response. All right, that's it for this one. I'm sorry, it's a long one.